Interesting. Hello, everybody. Sorry for the delay here. I'm used to hosting Zoom meetings where I actually see everybody, and as opposed to just seeing you guys over here on the attendee list. So give me just a moment to get set up here, and we'll get started. All right. Okay. Move some stuff around here. Not quite used to this format. Okay. So today we're going to talk a little bit about ANP row sensitivity, how it works and why it works the way it does. Also another why, which is why do you care about it in the first place? Excellent. Thank you very much, Pearson. Yeah, it's very strange doing it this way. It's hard to talk to people when you don't actually see people's faces. So please bear with me. I do have the Q&A section open, so if you guys have any questions, please let me know. I typically pause between slides to let you guys know that. Okay, so we're going to cover 5 things today, 5 basic ideas here, and we will. So the first thing is, why is ANP row sensitivity important? We're going to talk a little bit about why you would care about it. It does some pretty cool things. Not a lot of it's been published yet, but it's some pretty cool stuff. It's been around for a while. Second thing, after we get some reason why we might care about that, I want to talk a little bit about the ideas behind ANP row sensitivity, why it was created the way it was. It's there's some technical details around actually doing the calculations. And before we dive headlong into that, I want you to understand the reason it's set up the way it is. It's the most natural thing you could possibly do. But you have to see that it's the most natural thing you can do before you believe it. Next, I want to actually I'm going to go through 2 separate cases of the details of the calculation. One scaling things down and one scaling things up, and we'll see what that means in a minute. But we're actually going to go step by step through this. And then I'm going to recap, sort of talk about step 1 again in a bit more details. And I've got some example calculations together. And then throughout this, I'm using the PyANP library. So it's a Python ANP calculation library I developed a while ago. It's an open source library. You can create models with it. You can create multi-user models with it from a simple Excel spreadsheet. I'm not going to go through those details today, but I will go through doing some ANP row sensitivity calculations with this and just the general setup for it. Okay, so let's begin. So why should we care about ANP row sensitivity? Well, it allows us to do several things. One thing we could do with it is we could find the most influential parts of a model. So you've got a model with several nodes in it. What node is really causing the effects that you're seeing? That this one alternative wins, one alternative loses. ANP row sensitivity allows us to answer that question. What node is really the important node, or what nodes are the important nodes? We can also save time and everyone's patience. What this is talking about is, imagine a workflow like this. You have a model and you've got lots of connections in there. There's so many pairwise comparisons, people are going to go crazy trying to do them all. Well, we could simply do a bare bones basics diagonal, for instance, through it, minimal spanning set. And then look at marginal analysis, which is part of ANP row sensitivity, which will tell us the parts of the model that are most sensitive to changes. And what that tells you then is, I should really hone in and fine tune my pairwise comparisons on this node. The rest of them, some other nodes in there are going to be completely meaningless. So why bother going through all of the tedious comparisons for those when you don't need it? So we can use it for that. Understand the world from a single perspective. So in a tree, for instance, it's very easy to see if you've got a node down here. what the world looks like relative to that node. You just synthesize up to that node and you're done. And you can say, hey, that's what the alternatives look like there. In a network, we didn't have the ability to do that. With respect to this node, what does the world look like? But with ANP Row Sensitivity and a little playing around with the numbers, with the calculation, you can actually answer that question. For any node of the network, if that was the most important node in the network, what are your priorities for your alternatives? And another question, this one's actually due to Tom Sadi. The first time I was talking about this in a conference, he brought this idea up. So very cool idea. Let's say you have a model, and let's say, for instance, it's for an election, and your client, your candidate's losing. If you have a model that synopsizes the situation, we can use rank analysis, which is based on ANP Row sensitivity. What that will tell us is which node causes rank reversal first, if that node becomes more or less important. And what that tells you is you have to change. For instance, let's say it's the environment is the one. You have an environment node, and that node has the quickest rank change. What that tells you is if you can change everybody's perception of how important the environment is, your client can win. Let's say your candidate's very good on the environment, but it's not quite as important to people. If you can, rather than selling your candidate, if you can make sure people are really focusing on the environment, the importance of that will go up, your candidate wins. So it's using the model sort of in reverse. All right, let's pause here and see if there are any questions. I don't see anything on Q&A. For those of you who haven't used Q&A yet on this, I believe it's a button down at the bottom of your screen. There's a Q&A, pop up a window, and I think you can just type questions and ask me. All right, nothing. You can also throw them into chat if for whatever reason you can't find it. Okay, next. I want to talk a little bit about why it's different from AHP sensitivity. So this is the key thing here. You can look at an AHP model as if it's an ANP model with a super matrix. AHP sensitivity, when you're dragging the importance of one node in a cluster, it's trying to tell you, or you're changing the local priority there of that, which is really changing an element of the unscaled supermatrix. For a tree, at least, that's the same as a scaled supermatrix. But you're only changing one cell in that supermatrix. This works in the AHP setting because the supermatrix, if we're looking at it from the ANP world, that supermatrix is very sparse. It's got a ton of zeros and a few places with numbers in it. And so each cell that's not zero has a lot of importance. Okay, before I go on. Excellent. Next, in an ANP model with many connections, single entry. So once we have a matrix, super matrix with a lot of connections, with a lot of non-zeros, any one connection kind of dies out in the process. If you try and change it, which that's what the traditional sensitivity I created in super decisions had, was just changing one element in the super matrix. Turns out it's almost not sensitive at all, because everything else in that matrix is trying to keep things the way they were. And that one entry just can't fight against all those other entries. So if you think about just a small model with 10 by 10, 10 by 10 means there's 100 entries in that super matrix. You're changing 1 in 100 entries. It's not going to have that much effect. And experimentally, that was verified. We weren't seeing any sensitivity. Let me go back here real quick. Okay, so this is the reason why it's different from AHP sensitivity. We had to do something different because it wasn't working, trying to directly mimic AHP sensitivity, tree sensitivity. Okay, so quick refresher on the AHP version. Effectively, it's just changing the local priority. You've got a node with its children, and you change the children's weights. That's all it's doing. This is important. You change the weight of the priority of it. You're going to do the slider. It goes from 0 out to 1, making it the least important thing up to being the most important thing. And by the way, although this is just sort of looking at it locally, there's a way of thinking of it globally as well, so that you could change it not just from 0 to 1, but to be 0 to 1 across the entire global priority thing. It works very similarly. That's what I'm going to mimic at first here. So the two key things to think about, first of all, one is it's working on one node at a time. Two, it's playing with the priority of that node, setting it from 0 out to the most important thing. Three, that we can do that globally as well. All right, so we've gone through a little bit of the background. So now let's talk a little bit about the idea behind row sensitivity. The key thing is I want to mimic the AHP version as much as possible. In fact, this should be the AHP version when applied to an AHP tree or even a hierarchy. The key thing is this idea of moving the global priority from 0 all the way out to 1 in kind of that slider fashion. And we want to be able to change the supermatrix with the following ways. We want to make the priority of the node, be able to make the priority of the node go down towards 0, make it less and less important by changing the supermatrix. And then also be able to slide the priority up towards 1 by changing the supermatrix. And that's the naive idea. I want to mimic AHP sensitivity, but I want it to actually make a difference in that node by just working on the supermatrix. All right, any questions? All right, so next, axiomatic rules. So these are the rules I want ANP Row sensitivity to behave by. I want it to follow these rules. So I'm going to come up with a few simple axioms here. These are kind of weak axioms. I want to make slightly stronger axioms, more formal. So first of all, I'm only talking about supermatrix. There's a little subtlety whether I'm talking about scaled or unscaled. For the purposes of this talk, I'm only going to work with the scaled supermatrix, but there is a version that works for the unscaled supermatrix as well. But right now, we're just going to talk about the scaled supermatrix after you've scaled it by clusters so that the columns all add up to 1. There's a parameter p, so that p varies between 0 and 1. That's kind of like the local priority weight that you're sliding in the AHP world. I'm trying to mimic that thing. When p goes to 0, as I push p to 0, this is telling me it's kind of my placeholder for pushing the priority of my node to 0. And p goes to 1, the priority of that node should go towards 1. And in between 0 and 1, there's a value that I call the resting value, that the supermatrix is the same as I started. So in other words, I'll get the same priorities out. So there's pushing it towards 0, the priority of the node, pushing the priority of the node towards 1, and then there's the middle ground. And there's different values that this resting value can take. It's useful in different contexts, which one. So for the purposes of the calculations I'm going to show you today, 0.5, 1/2 is what we're going to use as resting value. So from 1/2 and below, I'm scaling down. From 1/2 and above, I'm scaling upwards. Okay, and the last axiom is we want to keep as many ratios as possible the same in the supermatrix. So if I look at any two entries in the supermatrix and look at the ratio of those entries, before and after I make the change, those ratios should be the same as much as possible. So if this entry was twice as much as this entry before, after I make my adjustment for sensitivity, it should be the same ratio as much as I can. I can't keep that everywhere. If I kept the same ratios, the matrix would be exactly the same. So I gotta break some ratios, but I wanna break as few as possible. So 3 basic axioms, only working on the supermatrix. There's this parameter. Great. So why should the ratio be the same? Excellent question, Pearson. So there's a basic premise of AHP and ANP when you're working on things is you're always talking about ratios. When you're pairwise comparing, A is twice as good as B. When you're looking at your global priority vectors, the ratio of those things tells you how much better one is than the other. So we want to respect that structure as much as possible. The super matrix has built into it this idea of all of those ratios. That's really kind of what it's storing, is the ratio of how important each node is with respect to a node, how important each other node is as a ratio. One is twice as good as the other, and then we scale it up appropriately. So we want the ratios to be the same because that's sort of the fundamental structure of an ANP model. Okay, hope that answered the question. All right, any follow-up? Thank you. So just from one of my fellow panelists, if you'd like to raise your hand, hopefully I will be pinged when you raise your hand. Let's see here, Q&A, I see it up here where I'm sharing screen, participants. All right, I can try and do that and see if I can see that as well. Excellent. All right, so I'll try and keep the participant screen up as well. All right, so what Rule 2 is really saying here is I'm just trying to behave like AHP sensitivity, that there's something I can do to slide down to make the thing less and less important, the node, and I can also slide it up to make it more and more important. All right, so now that's the naive idea. So we've gone through the first two things I was talking about, why we care about it, and the naive idea. So now we're going to talk, I'm going to tell you the rules for row sensitivity when you're sliding down. So this P less than P0 means I'm sliding it below. I'm going to tell you them. It's going to look a little strange, but then I'm actually going to do, I'm going to do a calculation where it'll all make sense then. So I'm going to write the rules down first, then we'll see it in a calculation and hopefully it'll make sense. So the idea here is if you look at your row, I'm going to take that row and just multiply every entry by essentially a fixed number to scale it down. So that'll make that row, for my node that I'm interested in, it'll make that row less and less important. That's what I'm trying to do when I'm scaling down, is make that row less and less important. And then every other row, so if I go column by column, if I look at a column, I rescale this entry, so it doesn't add up to 1 anymore. So I take the rest of the entries and rescale them so that all together that column will add up to 1. So there's just two things I do: rescale the row and column by column renormalize. And that's it. And we'll talk about the other case later. So just got a slight little hitch to it that's a little different. By the way, you can see if I'm talking about multiplying this row by a fixed number downward, if I do it all the way to 0, I would multiply that row. I would have P is 0, 0 divided by anything is 0. So I'm multiplying that row by 0. Essentially, I'm disconnecting that node from the network. It's not connected from anything anymore. So it's completely unimportant. Whatever happens there is irrelevant. So that's the idea. And you can see that it's scaling that row down, making it less and less important, making that node less and less important. Okay, so I know that this is without context, without a calculation yet, but are there any questions? No. Okay. Okay, so what about this P0 thing that I'm talking about, the resting value? I went over this a little bit earlier, but to reiterate, there are different values you can choose for your resting value. It's your choice. There's a smart P0, which I'll talk about in a minute. You could use the global priority if you wanted to. That works. Or use 1/2, which is what we're going to do. Smart P0, if you look at a graph for this, essentially it makes things work nicely on the graph, and I'll show you in a minute. All right. Give me just a second so I can answer that. All right. To make the arithmetic easier for us, we're going to choose P0 equals 1/2. You could use the global priority. That's also a reasonable thing to use. And the smart P0 is what makes It was created to solve a problem, and I'll show you that problem in a bit. All right, so if I'm going to do a calculation, I got to give you a model to work on. So here's my model. It's got 5 nodes in it, 3 criteria, 2 alternatives. The network is fully connected. And I'm not going to bother doing pairwise comparisons or anything else. I'm just going to give you the supermatrix. And this is the only time when I'm writing matrices that I'm going to label what the columns and the rows are. So it goes N1, N2, N3, 3 criteria, the 3 nodes, and then the 2 alternatives are at the end. And just for completion's sake here, we can see that the limit matrix, I calculated the limit matrix, it looks like this. And we see that the global priority for alt 1 is 0.098, and for the other one is 0.15. So definitely alternative 2 wins. And if you normalize those scores, you get that. So alternative 2 is almost twice as good in this setup. So 5 nodes, 3 criteria, 2 alternatives. Any questions? You can raise your hands if you'd like to speak, and I can give you guys the ability to talk. All right. All right, so the first calculation. So I'm going to scale down. I'm going to use our model. I'm going to do sensitivity on node 2. My windows are kind of blocking me here a little bit. The second row, in other words, and use this P0 as a half. And I'm going to scale it down so P is a quarter. So I'm halfway between 1/2, my resting value, and 0, which means my scaling value is going to be 1/2. That's what I'm going to want to multiply the row by. So this is the row that I'm scaling downward. So that row in red is what I'm going to scale downward. So that turns into, when I multiply by 1/2, I just take each entry and multiply it by 1/2. And when I'm done, I now have that entry scaled down by 1/2. It's a different row now. And my columns no longer add up to 1. So that's key. That's why I have to do some work on the columns. So the first job, by the way, you notice all my ratios in this row stayed the same because all I did is multiply each entry by 1/2. So all of these entries will be the same. All the ratios of all the other entries relative to each other will be the same because I haven't messed with them. It's just the ratios of things to this between this row and outside of it. All right, actually, let me go back. Questions on that? So all I did is multiply that row by 1/2. So I'm scaling that row. I'm effectively making the node N2 less important. Okay. So now I have to work on, I'm going to work on this column here. The first column needs to add up to 1. So for the other parts of that column, if I look back here, this added to, this is 0.24, so the rest of this had to add up to 0.76, which plus 24 would give me 1. I'm not going to bother adding them because I don't have to. I know that all of the other entries plus this one added to 24, so it has to be 0.76. So they originally added the other parts of column 1 other than the one I changed, added to 0.76. After scaling, now they should add up to 0.88 so that when I add 0.12, I get 1 again. So I need the rest, these other 4 entries, to add up to 0.88. They used to add up to 0.76. Now I need them to add up to 0.88. So I want to multiply all of those elements, all of these things in the red box here, I want to multiply by 88 over 76. So that's what I'm going to do. I've already made my change to this row. That row never gets messed up again. Now I'm making the changes here. And when I do, I get 0.88 over 0.76 is a little bigger than 1. So when I multiply by 0.48, I get something a little bigger. 0.08 goes to 0.0926. 0.04 goes to 0.0463, etc. And now this column adds up to 1. So I change the row, and now I change this column. But notice the ratio of these elements in this column is all the same still, because I multiply them all by the same number. Okay, now I got to do the same thing for column 2. So for column 2, I've got column 1 adding up to 1 now. Now I got to get column 2 adding up to 1. I've made my change here. The other 4 entries, I need to multiply them by something to get them to add up to 0.92, so that when I add 0.08, I get 1. Actually, before I go back, before I go through this one, I ran through this a little quick. Is there any questions on this? I don't see anything. Check the chat, see if anybody's hands are up. Nope, that's not where I'm seeing hands up. It's under participants. Don't see anything. Okay. So they originally added, by the way, they originally added to this column here, originally added, if I go back to the original version, it was 0.0. They originally added to 0.84. I now need them to add up to 0.92 to make this add up to 1, because I got a 0.8 here. So I have to multiply by that thing to scale those upwards, and I get this value. And I just continue doing the same thing. So that's the end of column 2. We go to column 3. They originally added up to 0.72. Now they add up to 0.86. So they have to add up to I need them to add up to 0.86, so that when I add this 0.14 that's here to 0.86, it would give me 1. So I need to scale these upwards to get it to 0.86, to get it to 0.86. Whoops, typo here, sorry. Copy and paste, this should be 0.86 divided by 0.72. I'll fix that. So, yeah, I wrote all the wrong things here, but I did actually multiply by the right numbers there on it. Sorry, I need to fix that. Make a note to myself here. All right, so I need it to add up to 0.91 now. It used to add up to 0.82. I need to add up to 0.91, so when I add this, I get 1. And I do have the correct scaling factors on this one. Yay. So here we go. Yes, Pearson, question. Let's see, if you raise your hand, I can allow you to talk. I think I just got to find you here. If you'd like to talk, or you can just type. Okay. Well, I guess not. I'll check, just try to type it and I'll answer when you get it there. So for this one here, I rescale it. They now add up to 0.91 after I make that change. Excellent. All right. Now the fifth and last column, let's see if I did this one correctly. So again, they originally added to 0.91 or 0.82. Now I need them to add up to 0.91, so this adds up. When I add this, I get 1. So I got to multiply by the same factor there. And when I do, I get this. And now I've rescaled my matrix. So this was what I originally started with. I rescaled this row and then scaled the columns appropriately. So I multiplied this row by 1/2, which gave me these numbers. And then I rescaled the columns, so I still had things that were stochastic that added to 1. So this is scaling downward. Any questions? That's fine. All right, and just so we can see what the results are, before my limit matrix turned out to be this with these alt scores. After, the limit matrix is a little different. You can see this row here for node 1, which was 0.2181, went down to 0.112, so it made a big difference. It didn't actually multiply it by 1/2, so that P is not quite directly changing it in that fashion, but it's close. But look at the alt scores. It didn't really make much of an impact. Slight one, alt 2 won a little bit more, but not a lot. Not much change. That's not unusual for scaling downward. Scaling downward tends to have less of an impact because if you think about it, I look at my original matrix here, any one row for any size matrix is always going to have entries that are generally less than a half, which means when you scale them down, you just don't have as much room to go downward. You've got a lot more room to go upward. So going upward should probably have more of an impact just because of that. All right. So now, what about scaling upward? It's not quite the same, and I want to do a quick example to show you why. So we could naively try to just like I did here, I could naively try to multiply this whole row up to get it closer to 1. But we have a problem. Not all the entries are the same here. Multiplying towards 0, as I get closer and closer to 0 when I'm multiplying, every entry goes to 0. But that's not true when I'm multiplying towards 1. So the biggest number I can multiply by is 1 over 0.28. And if I multiply this row by 1 over 0.28, which is a number slightly smaller than 4, I get to this, and I can't multiply by any larger number because if I did, I'd get a number here that's bigger than 1, and I can't have that in a stochastic matrix. Yes, so Beerson, scaling down doesn't have much impact, almost always. Occasionally it has some. Scaling upwards always has more impact. So, but when I tried to scale upward, if I tried to naively do the same thing I did before, I get a problem. I can't make this whole row go towards 1 this way. So, which means if I multiply anything by anything more than that, I get a number bigger than 1, which is not possible, but the row hasn't been completely pushed towards 1 to make it the most important. What do I do? Now this would be the place where if I had people in front of me, I would solicit suggestions more so. It'd be easier for people to shout them out. Unfortunately, we're not in that situation. So what do I do? So let me go back and look at, I'm just going to show you the matrix here. Before, what we did is we scaled down this row towards 0. That's what we were doing when we multiplied by our number a half, is we're scaling this row towards 0. What if, instead of scaling this row towards 0, I tried to scale this row towards 1 so that each entry went towards 1. In other words, what I want to do is I want to scale the distance from this row to all 1s down. And that's what I'm going to do is I'm going to take my row and I'm going to try and scale the distance down, scale that distance from 1. And when I do an example, we'll see. And then I just rescale the columns just like I did before. So that part's the same. This is the only difference when you're scaling upwards. So I'm going to use our model again. Same node, I'm going to look at it for the second row. Same resting value, but I'm going to go up to 3/4. So 3/4, by the way, is halfway between a half and 1. So I should be scaling the distance down from 1 by a half. So this number here, yes, absolutely. So I'll repeat this while I'm going through here. So this row here, what I want to do is I want to take this row's distance from 1 and scale it. So let's look through. So if I take that row and just do 1 minus that row, I get these numbers. 1 minus 24 is 0.76. So in other words, 0.24 is 0.76 distance from 1. 0.16 is 0.84 distance from 1. 0.28 is 0.72, then 0.82 and 0.82. So all I've done is just looked at 1 minus this row, and that tells me how far this row is from 1. So now I'm going to take those distances and scale them by a half. Take half of them. Okay, so half of 76 is 38, half of 84 is 42, etc. So these are going to be my new distances from 1 that I want my numbers to have. So the numbers would be this, because 0.62 is 0.38 from 1. 0.58 is 0.42 from 1. 0.64 is 0.36 from 1. This is going to be the new row here. So my 24, which was this 0.24, was 76 away from 1. I half that to get 38. And my new entry is going to be 0.62, which is half of this number's distance from 1. It's that much closer. So why do I want to do that? So back, remember in my axioms, I want this to behave like AHP row sensitivity. When I pull something out to 1, it makes it the most important thing in the tree when I do that. So in order to make this row, the most important row, the way to do that in the supermatrix is to make that row go towards 1. When that row is 1, everything else has to be 0 because it's because of stochastic. It's the only thing that matters. So I need to push that thing towards 1, but I want to respect ratios as much as possible. I can't quite respect the ratios here because if I did, I get into, if I did that, I get into this problem here, where if I just completely respect the ratios, I can't push them all towards 1. So instead, what I do is I push what I've done. If you notice, rather than respecting the ratios of these, I've respected the ratio of their distances from 1. So this one is 0.38 from 1. This one is 0.42 from 1, which the ratio of this to this is the same as the ratio of this to this. So the distance from 1, I am respecting that ratio. And that's the best that I can do if I'm going to try and push these guys towards 1. Did that help, Pearson? This is a subtlety. This is hard. I initially tried to do the other way first and ran into that problem. And so I had to think of something else. And this is what I came up with because ratios are important and because I know I need to get this row towards 1, the whole row, in order to make that node the most important thing in the network. Yes, and feel free to contact me afterwards as well if you have questions. So I've scaled the row, and now I got to scale the columns. And remember, I had to do it 5 times, and it was really unpleasant. It's easier now. I can do it in one fell swoop, one slide. So what I've done here is I've halved the distance. So originally, this column, for instance, added up to 0.76, right? It had to in order to make this add up to 1. It had to add up to this number, in fact. Well, my new one is going to have to add up to this number, which is half as much, which means I have to multiply each of these by 1/2 to get this to add up still. If I had to multiply each of these by 1/2, this will add up to 1. But the same is true for every other one also. Every one of these, rather than having to recalculate it every time, every one of these I'm going to just be multiplying by 1/2. So, and I'm just going to do that, and you'll see I take all of my numbers here that are in red and multiply by 1/2. And I get 2 plus 8 is 0.1. 24 plus 4.4 is 0.28. And then I've got, that's 0.38 plus 0.062 is 1. All I did is take each number and multiply it by 1/2. And voila. I halved the distance. I have to half these numbers. And this is my sensitivity scaling upward. So scaling the row upward, a little more complicated. Scaling all the rest of the entries is really easy. Excellent. So we're down to 10 minutes. So before, I had this Alt 2 1 originally. After, we're going to see something very interesting. Afterwards, Alt 1 wins by a mile. It wins by even more than Alt 2 won originally. Huge change. Huge change. Scaling upwards can make a very big difference. See, and you look at the limit matrix. Before it was 0.218 here, and now it's almost 0.6. Almost 3 times better, 3 times more important. So huge impact there. Okay. So huge rank reversal going on there. Scaling upwards can have that happen. It's much more likely when you're scaling upward to see a change. All right. Any questions about this? So this was a simple version of the calculation. I've got a paper out there from a while ago. Elena can put up a link to it as well on the conference page. But remember, ANP Row Sensitivity allows us to find the most influential parts, this ability to save everyone's time and patience, see things from a single perspective, and find where rank reversal happens. So, down to just a couple of minutes now. All right, so influence analysis, normally you use P0 as a half. And typically you pick a number below that you're going to slide it down lower, even though it's probably not going to have as much of an impact, and one above. And typically you choose them symmetrically. So if I go down by a half, up by a half, what happens? And then I just look at how much my priorities changed by. So that's exactly what I just did in this case here. I went up by a half and got this gargantuan change in alternative scores. And back before, I went down by a half and got smaller changes in scores. You look at how much they change by, and you do this for each node. And whatever node gives the largest change in priority scores tells you the node that has the most influence on your decision, or gives you an idea, at least, of the thing that has the most influence. Okay, questions? All right. Marginal analysis. So what marginal analysis is I have this P that I'm changing upwards and downwards. I can look at the slope of how fast things are changing at that particular point, at my resting point. In other words, if I just move a little bit, how much did I change by? Now, the interesting thing is the left and right-hand derivatives don't match up. Always, unless you use Smart P0. That's the point of Smart P0. Smart P0 slides P0 down, so these things that are meeting like this at P will go and meet flat as a smooth curve. And what I do is I just take it and move it a little bit up and divide by that. We'll look at each change and divide by that. Perspective analysis says take my P here and push it to 1 and look at what happens to the resulting priority scores, the alternative scores. So what that's telling you is if this node is the most important thing in the network, what wins? So in my example, talking about a candidate, if when I look at the environment and I push environment to being the most important, whatever candidate wins under that is saying, if the environment is the most important thing in the world to people, which candidate wins? In other words, that's why I call it perspective analysis. From the perspective of that node, what alternative wins? Okay, rank analysis is similar to influence. I move things up and down, but what I do is I move them up just enough until I cause a rank change. And how far I have to move it tells me how influential that node is in causing a rank change in alternatives. You could do it on just any old rank change, or you could say, well, what will get my alternative to go up a rank or down a rank? You can do it that way too. And whichever node has the smallest p-value closest to the resting value that causes a rank change, that's the node where you want to look at for changing people's opinions. Because if people have a different opinion about that, your candidate wins, or whatever alternative we're talking about. So it's where to focus changing the importance. So where you would put public campaigns out, for instance, to try and win. So this is turning the model on its head. Rather than the model telling us who wins, the model is now giving us insight into how to become the winner instead. All right. I can share a screen. I've got like only a few more minutes left. So unfortunately, I didn't get a chance to show all these calculations were done. I'll do just 1 minute of it at the end here. All these calculations were done with my ANP library. I've got a GitHub repository for this work. And for anybody else in the conference who wants to publish their code or anything else in this fashion, they can reach out to me or someone else at the conference, and we can put the code in there. My Python ANP library is available here. And here's my notes. And unfortunately, you're not going to see that because I'm not sharing the right screen. So I'll stop and I'll reshare. Screen whiteboard. I think is what I want. I think you should have this. So this is up there. This is where I was doing my calculations. Here's my initial matrix. And calculations printing out the super matrix and the synthesized scores. I created a little function to rescale the column entry by entry. So I scaled down the row here. And then I just called my function to rescale the columns each time. I did that both for scaling up and for scaling downward. And I compared it. I have a simple function that will do the row adjustment. So unfortunately, it hides that code sitting here on here. If it's got only one line of code, it doesn't show you. Let's see. There's got to be some way to open that through here. Let's see here. I can show it to you here as well. This is where it's actually running on my computer. Here's some influence scores. So I did for each of the first 3 nodes, 0, 1, and 2. I calculated the influence and found that node 1 has the far and away the most total influence. It changes alternative 1 up, or 1 up by 2, 3, 3, and down this one down by 2, 3, 3 for a net total effect of this. You can do other things though. For instance, influence table scaled, and I'll do it on row 1. And there is, so let me do quickly P0 mode. So you notice this is what's happening here is this is scaling the importance of node 1 down and up and all the rest of the alternatives. So in particular, 3 and 4 are the alternatives, the green and the red here. You can see as I scale it out, the green starts to win more and more. But you notice this break, this discontinuity. It's because I'm using the P0 as a half. If I don't, if I just use the default, which is smart P0, it sort of moves those back and to the point where it becomes continuous derivatives. Anyways, there's lots of functions around this. If you guys would like to see some examples, you can let me know. If you have some research work that you're working on that you would need something like this, I can certainly point you in the right directions as well. All right, I think I'm pretty close to time. I am right on time, in fact. So this right here is shared. So the URL for this is, real quick, I don't really have a second, but I will. If you go to github.com, WJLAdams, ISAHP2020, in the workshops, Dr. Adams, it's workshop.ipynotebook. And it's here, and you can copy and clone this. You can run the code locally on your computer. I've got some tutorials up on IANP.org, how to install So you would need to install Jupyter to get started. I've got a tutorial there on it. And I've got tutorials on how to do a few of the calculations, including some of the row sensitivity stuff. All right, Elena is going to punch me in the face if I don't stop talking because she has to get ready for hers. Are there any other questions I could answer in the last few seconds that I have? So again, if anybody wants to contact me, I think Elena has my email. She can send it out to folks. Anybody else who has any questions, please feel free to contact me. I'd be happy to help out. Don't mind at all giving you guys pointers on how to use the code that's out there. Okay.